What's up guys, how have you been? I'm really excited to present you this new tutorial video, especially for structural design engineers, for structural engineer specialized in steel design and calculation structure style. So today we're talking about a special software, IDEA Statica, which is this software, what can be used, what this software is useful for structural engineer, why structural engineers must know to use and master this software for a daily steel work detailing for every day. When you make a steel design connection detailing, why this software is very useful for you. The software is very useful for you because we're talking about many benefits in using it, but because you know how to manage design, checking, verifications according to different European or Asian code, American code, English code. So today we're talking about IDEA Statica. Why it's very important talking about Statica? Because we're talking about Statica in reference from different case studies of a success story of a different project made by software for join connection verifications. As you can see here, we're talking about the twist, the Christoph museum for the FAR, how you can model it, the workflow between robust structural analysis and IDEA Statica for a connection design and the joint verification manually and make the comparison. We're talking about this software and using this, how we can model it. I will show you how we can design a modeling, fit the modeling and make some calculation using robust structural analysis, and how you can put that difference connection. Why it's very important to talk about. It's very important to me to talking about the software because the software using as we call a CBFEM. CBFEM name is component-based finite element method. This method you will learn in using IDEA Statica how to use connection to design and code checking a structural style join case start of, for example, we're talking about connection of a tabular 3D frame. It's a synergy of a component method and finite element analysis. It's a unique method for design and code checking. We'll show how it's very important to present plates, bolts, and walls and all different members and anchorage and concrete, how you can make detailing for all different checking and verifications in using material nonlinear analysis, limit plastic strain, a bilinear material diagram, Young modulus, this depends of strain. So the most common material diagram which are used in infinite modeling of a structural steel are the ideal plastic and or elastic model with strain, learning and the stress. This diagram, if you have studying the stall design in my course in your academic courses, you must know what the meaning of this. So CBM come with some more important approach. This important approach is very useful for structural engineer because in generally enough to be usable for most of the joint footing and details in engineering practice. Simple and fast, exactly enough and daily practice to provide the result in time comparable to current methods and tools. Comprehensive enough to provide structural engineers with clear information about joint behaviors, stress, strain, reserve of individual components, and about overall safety and reliability. So the analyze FM model generated automatically. The design doesn't not create the FM model, they create the journey using manufacturing operations. So as you can see here, we show how to generate a report, how to design. This is the result generated, or we're checking everything here. We show you how to make all these things, how to generate, how to verify, how to add some loaded from import, because we're talking about the workflow, for example, for this a pedestrian and cycling bridge. You can see here the pedestrian bridge, how to design it and how you can, after from analysis and and verifying all structural analysis in robot analysis. When we arrive at the state to join and assemble verification and design, so how we can import some noise from robot structural analysis to IDEA Statica, and so how we can use this tubular 3D frame. So in verify in detail in using a component-based finite element method. So for our case, for this, we'll begin. When the software is there, we go to project, we create new projects. So we have all class of still a connection you want to do. So for my case, I will using this. And working with this blank connection, no connection, we can give name for your description, for, the name for your project. So you can choose directly here the bolt symbol, grade of concrete if you're using some conditions, the design code. As you can see here, we have the design code from European, we use Euro codes, American steel construction, ASCII, IASC, Canadian, UK, Netherlands, China, India, and so. So for our case, we're just using this. I'm created is a blank, or as is a blank. So this is our steel connection. Is a tubular 3D frame. Is a connection design of a tubular 3D frame. So the first overall is just to go to the property. For the properties, you need, as you can see for the database, there is no a type of a cross section profile still we want to use, because we want to working with pipe. So here we selected a shape geometry, and we have many kinds for CHS. So all. And you go to pipe. I'm using the pipe 310 model, and I have it. After here, the geometry type. There is two type of geometry in IDEA Statica: ended or continue. It will be ended, and the positions of my tube, I will change to this degree here, and duplicate this model, change, put name, and check, click OK, and after put here 0. We have a two symmetrical model, and after quickly I will change this diagonal. Remember, I'm using always the pipe favorite pipe, and I'm using the 100 std 152 std model. I'm clicking here. Okay, I have this model here. Then I will make some offset to make this more close. So I will change the gamma angle. I put 60 and make some displacements here of 50 millimeter. So for this case, I will change to using another pipe element. We change the size, and we'll put 244. Okay, and I have it. So after, I will duplicate this diagonal to have this member, and from this side I will put here 0, and I will change my picture from this. We have it. We put here 0, and I put minus this. So I change the value. This pipe and this diagonal, they have the same size, and this is another size. So this is the finish of our model. As you can see here,
we have this model, we have our model here. The IM is how we can put some loads and design it to make connection verification using IDEA Statica. So after to do it, we will add different loads from our connection element. I'm going to equilibrium to update the different member added. So I'm going to Excel. We can put it manually. If you're going to Excel, you can have some result coming from the Autodesk robot structural analysis from the selection of the node that you have selected to make some connection. So at this case, I will go to Excel. I have already my different load it apply for my different element of my connection. So I copy and go in here, I select it, paste. So as you can see here, we have already, because I don't want to add a second load table, I just replace the existing table. So I can see here we have all different loads apply for our different element. After to do it, the next step is to make the connection in using a bolt of this channel 1, the tube 1, the pipe 1 with the pipe 2. It's very simple. Do not think a lot. Do not complicate you from to lose time. It's IDEA Statica allow you to help you to saving time. So connect to, I select the element, the intelligent connection of the software Statica propose me this kind of software, this type of connection. I think it's very useful for me if I compare with the recent result of the recent model we have made. So at this case, I click here. I choose the bolt connection. I will be working with M30 and the class 8.8, the class of our bolt. After I'll make some parameters to make some modifications. So the positions are my position 340, 50. So I'm here, and you can make some measurement to see if it's corrected. So the thickness I'll put 45. I have this, and the radius it will be 40 to 250, and the inner radius will be 150, and the bolt, this is the plate, the parameter modifications of my plate. So for the parameter of bolt menu, here we have the type of our bolt, the radius minimum. For the radius millimeter, our radius will just increase the radius to have the possibility to see our bolt, because here we have the bolt because it's unknown. We can go inside, our bolt is inside our pipe. You need to increase the radius to make this show, to put it out of our tube. So I make 250. It's very great, and very big. I put 206. So that is okay. It is useful for me. Here we see our bolt with our class and diameter. So the number of our bolt, we put 12. We need to have 12 bolts. If you need, you can have a minimum of, but it's suitable for me to make this resistance between all this pipe. And after it can do after to do it, so we can change. For this case, my flange weld, from the weld parameter, I'll check and uncheck no weld from the flange positions. For the weld position, we'll add the trough, its thickness of 6, and I have it, and I can verify. I finish my connection between the two pipe with a 310 millimeter. So we're going. So the next step is to make some welding. The first welding will be between the diagram member 1 with the CH pipe. So going to member, excuse me, is not this. I delete operation, cut, and I select the first member. My first member will be diagonal 1 with cut by CH. And cutting method, the cutting method I will using surface. So here you can see our connections, and the second will be the diagram 2 with the CH. So I copy the same cutting operation method and change here to put diagonal 2 member with the CH. Directly we have it. The third cutting method, it will be between the M5 member with the CH. So M5 member with the CH. As we can see here, we have our kiting, and the last cutting operation will be between the D1 and D2. I select here D1 and the D2. Here we have our welding connections. So we must increase and check the flange and add 6 the trough thickness, and for the cut tree I make the same modifications, put 6, and the cut 2 and check and put 6, and the cut 1 and check and put 6. So I finish my connection, the 3D frame, the connection design of a tubular 3D frame. I finish this connection with IDEA Statica. For the manufacturing operation, the production of this connection will cost 209 euros. You can convert. So the software gives you some estimation about the operation you're doing in the software, and when you will going to the workshop, the factory, to produce in detail a factory the manufacturing of this element. After to do it, you have it. We already make everything here. The things stay to do is just to calculate, to verify if the all different connections, modifications we are doing in the software, it verify and it coding the code rule checking, a coding error code. So we'll see if we've doing the good connection. Of course, I'm really happy and excited to see everything is okay. Good calculation, good design analysis. The plate was going made, and the bolt was going made, and the weld was perfect made, no backling, and the calculate was made. So after to do it, you can see it a good connection. For in the reality, they're doing the same. You have the price, the number of the bolt. You can make some estimation quantities. So we can go into the check. To the check, it allows you to see what we are calling a CBFEM, a component based finite element method. Exactly for the classic method, I coming back here. From the classic method, you can see here where I'm doing it. Or excuse me, I didn't put it. Maybe I forget. So I'll coming with to see some illustrating of this the manual method and the numerical method. As you can see here, we have the possibility to verify everything. Checking, for example, for the checking, I can see I can check the equivalent stress. From the equivalent stress and applying from my equivalent stress, see my bolt. I can see my different bolt in erection between bolt and plate, in erection between plate and tube. So you can see here there is some enough stress here, so you need to make some reinforcements, or we can add some trough thickness for the welding for this space. As you can see here, we can go the mesh of our element. The things that you can see it in using the manual method, or the recent method, or the usual method, because actually it's the innovation in the 3D steel connection detailing, design, and the verifications is very, it's good software. You can put some deformation. You see how your element is deformed, and you can verify from different elements, CBM element, CBFEM. You can see plate here. You can see the behavior of your plate. You can locate the Z. You can locate the area, and for the bolt, you can see here which size of the bolt. There is the presence of many high stress. You can see here the component, the behavior of your structure from different loads applied in the reality. So it will give you some idea about what you want to doing to modify before to make it on the execution on the seat. And here you can see some manual calculation verification according Euro code 3. So if you want to make some hand or manual verifications, you can go into this page and table 3.4. You can verify and the meaning of each value of each letter of each element, a factor, its tensile structure of the board, tensile structure of the area of the board, shaft factor, the punching resistance checks. We can do it manually, but software is very fast. It's very accurate. A shear resistance check, a bearing resistance check, and so we can see all different elements. For the weld, it gives you the same. So you can make some capture, you can make some capture screen from the presentation, as I did from my presentation of today. So you can go far. You can verify the deformation, the plastic strain. You can see here, and it can give you some elements, and you can see everything is here. After to make this all verification, you can see some apply load from different bolts. So you can back at this, and so you can go. You can verify the stress in contact. The stress in contact will allow you the varying stress from different elements, bolts, weld, plates, and other members. You can go here, contact stretch, and they make some verifications. You can see, as you can see at this side, there is some very contact between this element. The amount of high stress is about the extremity here. So you can see how you can make the eccentricity of your bolt, how you can manage it, change it, and change the positions. After to do this, you can go to the report. So report will give you the general detailed calculate notes. You can use it for the presentation, for the project, and use it for the execution. That is very important. It was a pleasure for me to talk to you, explain about this. It's the first time to talk about this software, but I think for the in the future, for this year, there is some surprise. We're talking deeply in details with this software, his connection, workflow beam with other structural software like Robo, ETABS, MyDays, Sophistic, double FEM, and so there is many kinds. CI engineer, this is a not calculate, and so it was a pleasure for me to present you this tutorials who have been talking about the connection design of a tubular 3D FM in using component-based finite element method. Thank you so much. See you later for the next tutorial video. We're talking about other future structural engineer. Thank you so much. Have a nice day. Bye bye.